Swayam Prabha. Digital India. Educated India.
Last few lectures we have looked at how to get the static and kinematic indeterminacy of a structure. Then we have reviewed the basic concepts of the principle of virtual work, and after that we have actually looked at applying the virtual force method in getting the response of statically indeterminate structures using the force method. Anyway, the whole point is you should have already been exposed to the force method. I just spent some time looking, reviewing, and especially using the principle of virtual work to set up the equations. Today we are going to be taking up a truss example and going through the entire procedure for a particular, as I promised last time that I shall be looking at realistic example problems, and today that's what I'm going to be doing. I'm going to take a realistic problem, a truss problem, and then go through with the entire analysis procedure and get the answers so that you would be able to understand all the steps that go through in using the force method for a truss example. Next lecture I am going to be taking up a beam and a frame example so that we can walk through not only the procedure itself but the steps in the procedure so that you can get whatever it is that you are being asked to find out. Okay? So let us now look at the truss example. This is a typical truss bridge that you are likely to see if you have ever traveled by train on a railway bridge. Of course, what I have done is typically you have many panels in a railway bridge, and I have just taken 4 panels, 1, 2, 3, 4. Each panel is 5 meters length, and therefore the total span of the bridge is 20 meters. Okay. And if you look at the height of the bridge, this is 5 meters. This is typical, the 5 meter length is a typical length that you would see in most bridges in India. Okay. And the only thing that I have done is I have taken the panel, the BCFG panel, and I have put 2 diagonals in it, and I have taken the CDGH panel and I have put 2 diagonals in it. Okay. So these are the end portal, these are the verticals, these are the diagonals, and this is the bottom chord and the top chord. So BCD is the top chord, AFGHE is the bottom chord, and BF, CG, DH are the verticals, AB is the end rekha, AB and DE, and the diagonals are BG, FC, CH and GD. Okay. So you are given that there is a loading 150 kilonewtons at F, 200 kilonewtons at G, 150 kilonewtons at H. So this is the loading, and you are also given that all the members have an area of 2000 millimeters squared, and the E value, this is steel, so it is 200 GPa. Okay? And the question is, find the forces in members due to the loading alone, and the second part is find the forces in the members due to a temperature effect only. Okay? The temperature effect, the top members A, B, BC, CD and DE, these are subjected to plus 25 degree Celsius increase in temperature, and alpha is given as 1.2 into 10 to the power of 5, which is the coefficient of thermal expansion for a steel member. Okay. So this is the entire problem, and this is what you have to find out. Okay. So now if you look at this again, let us first find out what the static indeterminacy of the structure is. For that, let me draw the structure again. This is the structure. Okay. So we have to find out the static indeterminacy of a truss. First and foremost, find out the number of members. Members is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So number of members is 12. Okay. Number of support reactions, 1, 2 at the hinge and 3 at the 1 at the roller, so total 3. And now we have to find out how many joints there are. 1, 2, 3, 4, 5, 6, 7, 8. One, 2, 3, 4, 5, 6, 7, 8. Okay. So if you look at it, how many members do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So we have 15 members. I missed the 3 verticals when I was doing the computation. So there are 15 members. Okay. So let us look at it. So how many unknowns do we have? For each member, one force, the actual force in the member is an unknown, and the number of reactions are unknown. So total number of unknowns are m plus r, which is 15 plus 3, which is equal to 18. And number of equations are 2 for each joint. So it's 2 into 8, 16. So static indeterminacy 2. So the static indeterminacy of this problem is 2. And therefore, we are required, so you see we are going through all the steps that we have. We are going through all the steps. In that we have first the computation of the static indeterminacy of the structure. Once we have the static indeterminacy, then we find out the number of redundants. Redundants are those which, if we put equal to 0, then we have a stable statically determinate structure. So let us look at that. In this particular case, this is my x1 and this is my x2. Okay. So these are my members. So if I look at it, therefore, then my base structure, if I look at my base structure is please note that my drawing is not very good. So actually this member and this member are the same size because the panels, this and this panel size is the same. Okay, so this is my base structure. Okay, and now I'm solving the first part of the problem, which is forces in the members due to loading. So let us look at that. Let us put the loading. (150), 200, 150. Okay, so this is the loading. Now I need to, since this is a statically determinate structure, I need to find out all the forces in all the members due to the loading alone. Okay, so if we look at it, if we see sigma Fx equal to 0 gives me this, and sigma Fy equal to 0, and taking moments about any point, you will see this is symmetric loading. So therefore, without much ado, I am going to write down the reactions. So if you look at the reactions, then this is 250, 250 here, and 0 is the horizontal thrust here. And so once we've done that, we can actually start solving for the structural loading. And therefore, if you look at it, I can start at this point. Let me just put down, this is A, B, C, D, E, F, G, H. Okay, so taking the method of joints at this point, we will see that this is equal to, because the vertical component of it has to be equal to this, and therefore the horizontal component of this is equal to this. So this is 250. Now if we go over here and take Bohm method of joints here, this turns out to be 250, and this turns out to be 150. Okay, so once we have that, then again I can actually go everywhere, but I'm just saying, if I do this here, this will also turn out to be 250 over root 2. This is going to be equal to 250. Similarly, this will be 250, and this will be 150. Okay, and once we do that, we can find out the forces in these members also. Without much ado, I'm just going to go ahead and do this. And if you look at this, this will turn out to be, you see, the vertical component of this has to be, of this member has to be equal to this minus this. So if you really look at it, this will become 100 root 2. And if we do that, then this becomes 350. If you take moments at this particular point, this member turns out to be a zero force member. This one is 350, and similarly, because of this is 100 root 2. So I've got all the forces and all the members. So now the thing is that what we need to do is, what's the next step? The next step is, see, remember that these members are cut, but they still exist. Remember that always, that we know that the forces in these members are 0 because we have cut them. However, the members still exist, so I should actually put it down as 0 and 0. However, one other point, that again I am going back, how do we get the additional equation? See, we have 16 equations and 18 unknowns. So we actually need 2 more equations so that we can solve for x1 and x2. How do we do that? That is by actually finding out the displacement of these 2 points relative to each other, given the loading and also given x1 and x2. Once we find those out, then we can solve for find out the compatibility condition over here will be that this displacement has to be equal to 0, and the compatibility condition here is the displacement has to be equal to 0. So that gives us 2 additional equations, and once we have those 2 additional equations, we can solve for them, get x1 and x2, and once we get x1 and x2, we can the structure can be, all the member forces can be found out. Okay. So now what I want to do is, so that is all the forces in the members. Okay. Now how do we find out the displacement at that point? Now I want to introduce one concept, and that is that if you note that all I need to do, just look through this, I need to actually solve 2 other problems. Let me go through it and then I'll explain to you what I am doing. What I have done here is that I need to look at 2 additional analyses. Okay. If you look at this, what does this represent, this analysis? Here what I have done is, corresponding to the redundant force, I have put a unit force here, and corresponding to the second redundant force, this is 0. The second structure has the force corresponding to the first redundant as 0, and the force corresponding to the second redundant as 1. Okay. And I claim that if I solve these 2 additional equilibrium problems, I should be able to analyze this structure. Now let me explain how that is. Let's look at this. One of the first things is to the compatibility. For the compatibility, I have to find out the displacement at this point due to the loading plus due to x1 plus due to x2. You see? So actually the displacement at this point I need to find out under this loading, of course not equal to 1, equal to x1, and under this loading where x2. You see, if you add this and this and this with this not 1 but x1 and x2, then you see that is the structure, actual structure that you have. And this point is, therefore what you are trying to do is again use superposition, find out the displacement at both the cuts due to all the loads, and then sum them all up, and that will give you the actual displacement. Okay. Now the loading we have done. Now in the loading, if I need to find out this displacement, and I am using the principle of virtual displacement, what would I do? I would use a virtual force system where this was equal to some arbitrary value. I might as well take it equal to 1. Okay? Now if I wanted to find out the displacement here, what would I have to do? I would have to find out, take a unit force corresponding to this, and then find out the work done. So this would be the virtual force system to find this displacement. This would be the virtual force system to find this displacement under this loading. Now furthermore, under this loading, I need to find out the displacement here. So under this loading, you see this problem, okay, again is the same loading, excepting that it's not equal to 1, it will be multiplied by x1. That will give me the displacement at this point. So the real force system is this, and for finding out this displacement here, this is the virtual force system. For finding out the displacement here, this is the virtual force system. Then to find out the displacement here, okay, due to this loading, this is the virtual force system. Okay. Now let's look at this particular case. In this particular case, under this loading, if I have to find out the displacement here, then this is the virtual force system. Okay. And if I have to find out the displacement here, then this itself is the virtual force system. You see, so therefore the point that I am trying to make is that as long as I have these three, this one and this one and this one, equilibrium, I can actually get all the variety of things. Okay. So therefore I am going to solve for this, and I am going to put equal to 1 here, because if it is the actual load, then all I have to do is find out the forces here and multiply it by x1. That is not just the forces, even the displacements I get here, I multiply by x1 and I get the actual displacements due to x1. Okay. Now here is where I am going to introduce, first let me solve these structures, and then we will go on to seeing what is there, what additional points that we have to note. I am going to make a general kind of development on the theory that we have already done, where is the displacement plus displacement equal to 0. So I am just going to put that down in proper format, so that you get the complete way of solving all problems. So first let me analyze this problem. So under this loading, it is obvious, since there is no external loading, sigma fx and sigma fy and sigma m equal to 0 around any point shows that these reactions are 0. If these reactions are 0, then these member forces automatically are equal to 0. Okay. So if you look at this, here also this is the force, right. So this is force equal to 1. So if I take the vertical component of this at this point will be taken by this. So therefore this is going to be equal to 1 over root 2. Okay. And then the horizontal component of this will be taken by this. So this is 1 over root 2. Okay. And then again, if I look at this point, this is equal to 0, this is equal to 0, and then since this is equal to 0, this will be equal to 0, and so is this equal to 0. Okay, because if you look at this, so since this is equal to 0, now at this particular point we have to be careful to see what are the other forces that we get. Okay. So now let us look at something where we know. Okay. So here what we have is which is the point. Do I know all the forces? I don't know all the forces. There are 3 unknowns here. So which place should I go to? I will go to this point where I have 2 unknowns. So if I look at this particular one, the vertical component of this is going to be equal to this. Okay. So therefore if I put that, you will see that this will be equal to 1. Okay. Then if you look at this particular one, the vertical component of this is equal to horizontal component of this. So this is going to be equal to 1 root 2. Now let us look at where do we go here? Now here, do we know 3? Yeah, we know 3 of them. Okay. So if you look at this particular one, okay, I know 1, 2, 3. So I have only 2 unknowns. So I can solve for them. Now if I look at the vertical component, does it give me anything? No. Okay. Can I look at the horizontal component? Horizontal component, this one does not contribute, only this contributes. So if you look at this, the horizontal component of this is 1 over root 2, and this is opposite, so summation equal to 0. So therefore this force has to be equal to 0. Now if this force is equal to 0, then only the vertical component of this comes in here, and if we look at this, this becomes 1 over root 2. Okay. So therefore, and now let's come to here, this point. Okay. If we come to this point, I know this force, I know this force, I know this force, I know this force, so I just need to check whether this will come out. So what will this be? The horizontal component. If I take the horizontal component of this, I get minus 1 upon root 2, so this becomes equal to 0. If you look at the vertical component, this is 1 over root 2, check. Everything checks. And if I come over here, all forces in the members are 0, so therefore it checks. Okay, you will always get 3 checks. So here I have got sigma fx and fy equal to 0, and here I have got sigma fy equal to 0. These are the 3 checks that I have in this entire procedure. Okay, so that means these are the forces due to this application of x1 equal to 1 and x2 equal to 0. Similarly, if I apply x2 equal to 0, x2 equal to 1 and x1 equal to 0, then just we get exactly the same kind of thing. Only thing is that on this side, because of this x1, these panels are non-zero and these panels are 0. Here you will just have the opposite. These panels are 0. I am not going to go through these steps. I will request you to go through these steps yourself. As I said, analysis is not something that I am going to be doing. Okay, so I am just writing down the values. Statically determinate analysis, you should already be totally used to it. Okay, and then this is 0, this is 0, and this is 1 over root 2. Okay, so I think that essentially anything. Oh yeah, this is equal to 0, and this is equal to 1 over root 2. Okay, I think that takes care of it. Those are the 2 analyses. Now, having done these 3 analyses, let me write down all the values that I have in a particular pattern. Okay, I am going to write it down in a table, and so this table I am going to make. First, the table will have member. Okay, so members here. Then I am going to write down the load. This I am writing down is the load, is the actual force in members due to the loading. Okay. Then next I am going to write down, and I will call this P1I. This is the force that I have got in the members due to x1 equal to 1 and x2 equal to 0. So these are what I call as P1I. I will explain to you why I call it P1I, and then this I will call it as P2I. So I am going to write it down as P2I, and let me write them all down. Okay, so I have member AB, then I have member BC, then I have member CD, then I have member DE, then I have member AF, BF, BG, FC, FG. I'm not going to be able to write down all the members here, okay, but you understand the point that I'm trying to do here. There are a total number of 18 member forces, so I have to actually put it down. FG, then I have CG, then I have CH, then I have GD, then I have GH, DH, and HE. How many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Yes, correct. So I have 15 members that I have here, and I'm going to write down the values of the loads that I get. In member AB, I got a compressive force, so I'm going to, compressive force for me is going to be equal to negative, so this, and then in this load, I'm actually just to explain to you what I am doing is, let's see, I'll just show you one thing, that what is AB, member AB, 250 compressive, okay, so that's all I have done, minus 250. Then if you look at this, AB, in this 0, in this 0, so 0. So all I am doing here is actually just putting down all the values for you. So this is going to be compressive minus 350, here this is going to be minus 1 over root 2, and in this case 0. This is CD minus 350, then 0 minus 1 over root 2, and then DE, I have DE is minus 250 for the loading, for this it is 0, and for this it is 0. AF is plus 250 because it's tension, and in this case AF is 0, in this case it is 0. BF is plus 150 here, minus 1 over root 2 here, and 0 here. BG, if you look at it, it's going to be plus 100 root 2. Here BG is equal to 1. In here BG equal to 0. FC is equal to 0 here, because that is FC is x1. So here it's going to be 1, and here it's going to be 0. This is FC is the force here is x1. So obviously it will be 0 here, 1 corresponding to x1 equal to 1, and 0 when x1 equal to 0. FG is plus 250 here, then it is minus 1 over root 2 here, and 0 here. CG is going to be equal to 0 here, okay, minus 1 over root 2 here, and minus 1 over root 2 here. CH is going to be CH is equal to x2. So this is going to be 0 here, 0 here, and 1 here. Okay. So if you look at this, for x1 0 1 0, for x2 0 0 1, obvious. GD is going to be equal to 100 plus 100 root 2 here. GD is going to be 0 here, and is going to be equal to 1 here. GH is going to be plus 250 here, it's going to be 0 here, and it's going to be minus 1 over root 2 here. And finally, I have dH. dH is plus 150. Here dH is 0. Here it is minus 1 over root 2. And finally HE plus 250, 0, 0. So these are all the members that I have. Now, you see, understand this, that this is the real loading, okay? This represents, so in the real loading case, if I want to find out the displacement corresponding to in FC, the separation, then what is my virtual displacement pattern? This one, okay? And if I want to find out the displacement corresponding to x2 in CH, this is going to be the virtual force, okay? So therefore, if I look at it, therefore, here I am going to now put it down on paper that virtual displacement gives me, in the first case, 1 into delta 1, 0. What is this delta 1, 0? This is the separation at this separation, okay? So for this is my virtual displacement pattern, where I have put x1 equal to 1, okay, x1 equal to 1. So therefore, for that one, the virtual work is going to be 1, that's the virtual force corresponding to delta L1, into delta L1, delta 1, 0, is equal to summation over all the members I, okay, and on each member the deformation. What is the real deformation? Real deformation is the real load multiplied by Li upon Ea. Note that Ea here is the same for all the members. This is the real deformation multiplied by the virtual force, which is going to be equal to P1I. Is that clear? So therefore, you understand that delta 1, 0 is nothing but summation of, now since Ea goes outside, because Ea is the same for all the members, so this is going to be equal to P1, P1I, Li, that's all. So that gives me delta 1, 0. How do I get delta 1 x? Delta 1 due to x1. Delta x1 is going to be equal to, let's look at it. This again, here the real load is going to be P1 x1, because note that P1 x1 gives me the forces in all the members due to the load x1, the real load x1. So this is going to be this load into Li upon Ea multiplied by, now this is the 1, so therefore this one, the virtual force pattern is going to be P1I, okay? So therefore, if you really look at this, this turns out to be equal to, now the x1 and Ea are independent of each other, so I can take it outside. So I get x1 upon Ea inside P1I squared Li. Okay. Now, what do I want to find out? I want to find out delta 2, 1, that is the load corresponding, the real load is x1, and I want to find out the displacement corresponding to x2. So if I look at this, now I am just going to write these down. I don't need to talk about them anymore. The real load is 1, so the real is P1I into x1 into Li upon Ea, and the virtual load is P2I, because that's the displacement that you are finding out. If I put this in, I get x1 upon Ea summation P1I, P2I, Li. Okay, and in this fashion, putting down all of these, I can put them down in this fashion. Using the virtual work, I've got delta 1 is equal to 1 upon Ea Pi P1I Li. Delta 2 0 is equal to 1 upon Ea summation Pi P2I Li. Delta 1 1, this is due to x1, is going to be equal to x1 into 1 upon Ea P1 squared Li. Sorry, the Ea is already outside, so the Ea is not required. Okay, of course, if Ea is not the same, you can put Eai inside also. Then delta 2 1 is equal to x1 into 1 upon Ea P1I P2I Li. Delta 2 2 is equal to x2 1 upon Ea P2I squared Li, and delta 1 2, there's a displacement at 1 due to x2 is going to be equal to x2 1 upon Ea summation P1I P2I Li. Now if we do this, let us look at what this represents. What does this term represent? This term represents the displacement at 1 due to a unit x1. Okay? Displacement at 1 due to a unit load x1. Okay? That can be defined as a flexibility coefficient 1 1. What is flexibility coefficient? Understand, displacement due to unit load is what? Flexibility. And I am putting down F11 because that corresponds to delta 1 1. This is the displacement at 1 due to a unit load at 1. What is this? This part, if you look at it, is displacement at 2 due to a unit load x1. So F21. What is this? Displacement at 2 due to a unit load at 1. What is this? Delta 2 2. Load displacement at 2 due to load at 2. So this part is equal to F22. Displacement at 2 due to a unit load at 2. And this part is equal to F12. Displacement at 1 due to load at 2. So this will be displacement at 1 due to a unit load at 2. All these are nothing but the flexibility coefficients for this structure. So if I put them together, you will see I can rewrite this equation in this manner. Delta 1 0, this is the displacement at 1 due to the loading, plus F11 x1, displacement at 1 due to unit load multiplied by the load itself, plus F12 x2, displacement at 1 due to the load at 2 unit load at 2 multiplied by x2. And this, if you look at this, what is this? Displacement at 1 due to loading, displacement at 1 due to x1, displacement at 1 due to x2. And if you add all of the three up, that is the original structure, right? This is the displacement in the original structure. What is the displacement in the original structure? Those 2 points cannot move. Okay? So therefore the displacement in the original structure is this. Now let's look at the second compatibility condition. This is the compatibility condition corresponding to the first load. So that here what I am saying is that at this point, due to summation of all the effects, these 2 points cannot go apart because Fc is actually a member. Okay. So then next, similarly for the other one, F21 x1 plus F22 x2 is equal to 0. Okay. Here if you look at this, this is displacement at 2 due to the x1, because due to unit multiplied by x1, this gives me the displacement at 2 due to x1, displacement at 2 due to x2, displacement due to the loading, all of them together add up to 0. These are my compatibility conditions. And I can solve for these to get x1 and x2. So if I look at this one I can rewrite in this fashion: F11, F12, F21, F22, x1, x2 equal to 0, 0. Okay. Now for this particular structure, I shall write down the Li. The only thing that I need to do over here is write down what the Li are for each, and then all I need to do is just multiply all those values. Okay. I've got note that I can, once I find out P1i, P1, P1, P2, Li, I can find out all these coefficients, and I'm going to do those. But first I'll write down the Li, and if you look at the Li, okay, this is going to be equal to AB. AB is going to be equal to 5 root 2. BC, BC is going to be 5. CD, CD is going to be 5. DE, DE is going to be 5 root 2. AF, AF is going to be equal to 5. BF, BF is going to be equal to 5. Okay. And then if you really look at it, next we have BG. BG is equal to 5 root 2. FC, FC is equal to 5 root 2. FG, FG is equal to 5. CG, CG is equal to 5. CH, CH is equal to 5 root 2. GD, GD is equal to 5 root 2. GH, GH is equal to 5. DH, DH is going to be equal to 5. HE, HE is going to be equal to 5. So I have got all my displacement lengths, etc., and I can now do all of these computations. I will write down the values for you right now, and then so therefore in this particular case delta 1 0 is equal to 823.22 upon EA. Delta 2 0 identical because this is a symmetrical structure, 823.22 upon EA. And F11, F11 is equal to 24.19 EA. F22 is also the same, 24.19 upon EA. And F12 is equal to F21, it's equal to 2.5 upon EA. This is not equal to 0, this is equal to minus delta 1 0 and minus delta 2 0. These terms come in here. So this is the equation. Here I know F1, F12, F21, F22. I know delta 1 0 and delta 2 2, and I can solve these equations for x1 and x2. I'll actually write down the values of x1 and x2 for you, and they turn out to be equal to x1 is equal to x2 is equal to 30.9 kilonewtons. Okay. So now how do I find out the force in all the members? The force in all the members are going to be equal to Pi plus P1i plus P2i x2. I can find out the force, actual force in all the members in this fashion. Okay? This is in the actual structure. Okay? So much for all of this. Now I want to end it by talking about one very fundamental point over here, and that is that you see that F12 is equal to F21 in this particular case. Is that true always? Is that always true? Now you will see that what does F12 represent? F12 represents the displacement at 1 due to unit load at 2. And what does F21 represent? Displacement at 2 due to unit load at 1. Now let us look at this. What is this? If you really look at this, that displacement at 1 due to unit load at 2, so that means the loads in both the cases, in one case it is applied at 2, in one case it is applied at 1, the loads are the same. So what can we say about the displacements? Let us go back to the Maxwell's Betty reciprocal theorem. If you really look at that, what does that say? It says due to a load at 1, the displacement at 2 is equal to the displacement at 1 if we apply the same load at 2. That is what reciprocal theorem. So therefore, if you really look at this, the same load is being applied, 1 unit load. Once it is being applied at 1 and we are finding out the displacement at 2, and in one case we are applying the load at 2 and we are finding out the displacement at 1. Obviously they are going to be the same. Okay? So therefore, this is a fundamental fact that the coefficients F12 and F21 are always equal to each other, always. And in fact, we can make this general. We can say that this is always the case. If that is the case and these two are equal to each other, what can we say about this matrix? This is a symmetric matrix, and this is always true. The flexibility matrix is always symmetric. Okay? Now this is due to the load alone. Now we also looked at how to get the for the temperature. I am going to leave this for the next lecture as to how to compute x1 and x2, and then of course all the member forces due to the temperature in the members AB, BC, CD and DE. Thank you.